Hi everyone, my name is Kai Chungying. I'm going to present the final project application code. For this project, we basically need to forecast hourly temperature based on every previous 24 hours timestamp. So as you see here, there are several sections in this report, including the import data, data cleaning, EDA visualization, data normalization, transformation, modeling, forecasting by LSTM model, and then export the prediction value for KO submission. So this is the IPython environment. So we just can click on the cell tab on top and then click run all below. Then all the result will be output accordingly. Let's jump to the first part. The first part, we're going to import the data and clean the data. As you see here, we're going to import the data set to data frame format and check the range timestamp, which is from 2009 to 2017, January 1st to January 1st. And then we're going to use the datetime column as the index of the data frame. And then we're going to check on the missing value of the data set. In this case, there are no missing value. Next, we are going to do the EDA and visualization. We first start to check on the mean value of the temperature of each hour, and also run the hypothesis test to verify which hour has the highest and lowest temperature. In the hypothesis test, I resample the temperature value for some of the hours, like hours 14, 15, 16, and hour number 4, 5, and 6, and calculate the confidence interval for each one of them. By doing that, we can confirm which hour should have the highest or lowest temperature. The final result proves that the hour number 15 has the highest temperature and the hour number 5 has the lowest temperature. And then we are going to check on the correlation between features and target values. As you see in this heat map, the features T-port and T-geo are highly correlated with the TDVC, which is our target values. And the features VPAC and the SH are highly correlated with the H2OC features. We could observe on the results of training process and consider to eliminate some of the highly correlated feature afterward if the training result is not accurate enough. And then we are going to check on the features values changes over time and see how the patterns of target prediction values T-degree reacts against other features. Based on the above correlation values, we could observe that T-degree are highly correlated with features T-geo and T-port, and the patterns shown here are matching those values. And also, we could observe that features are mostly have seasonal patterns, which we could keep our eyes on to see if the same effect apply on our prediction as well. And then we are going to take a look at the statistics and distribution of each feature. We could observe that there are outliers in each feature. In this experiment, we are going to save them because we are dealing with the time series, so that we want to observe if there is any particular values impact on the target values in particular time period. Next part, we're going to take a look at the Bollinger Band plot. This plot basically tells us that the actual target value T-degree mostly falls within the range of 3 times standard deviation with 24-hour windows. The upper bound is in blue, the lower bound is in green. The red is the actual temperature. Let's see if we need to apply this finding to the machine learning process later on. The next part, we're going to do the data normalization and transformation to prepare the data set for training process. We first reload the data set and then split the data set to train and test set, and then turn the data frame to LSTM array format, which includes 336 features on each row. That comes from the timestamp 24 times 14, which is the original features in each row. And that's the train set, and this is the test set. And then and transform the target prediction values to time series format, which is in array format, and then normalize the data set in range of 0 and 1. That's the train set, and that's the test set. And then transform the data set to LSTM time series structure, 2D to 3D. So we split the 336 2D data set to a 24 and 14. 24 is the time step, and 14 is the original number of features on each row. And then we're going to take a look at the modeling and forecasting, which is the main part of this project. we use the LSTM model technique to do the prediction. First of all, we're gonna import all the libraries from the Keras module, and then set up the network. This is the best network that I have. 4 layers, 2 layers LSTM with 16 loops, and then 2 layers dense, 8 loops, and 1 loops. For the first LSTM, we set up the acceleration function as tangent, which actually is a default acceleration function, and then the input shape is timestamp times the number of features, which is 24 timestamp, and number of features 14, and then set return sequence is equals true, and then kernel set as normal, and the acceleration function set as linear. After that, we're gonna set up another function called model checkpoint, which is the function to save the best model during the training process based on the best validation loss. And then we compile the model network by passing in the loss MAE function, and then set an optimizer as atom. For this particular network, I set up the batch size equals to 200 and number of epoch equals to 1000. And then we're gonna feed in the chain set, and then evaluate the test set. This line here just save the model from the very last epoch iteration, and this right here just save the history to a CSV format with 3 columns: number of epoch, chain loss, and validation loss. And let's take a look at the training result summary. I basically have 5 different models, and like the first model, I set up the batch size equal to 200, and then epoch equals to 500, and then loops in the LSTM layers 8, 14, 32, and then 2 layer LSTM, 1 layer of dense. Set the acceleration function as default, and then this is the loss for the training set and loss for the test set. And then the second model is basically similar to the above, but just add the dropout function to the model 2. And then model 3, I set the acceleration function as linear in the dense layer, and then normal set for the kernel in the dense layer as well. And then set for model number 4, I basically the model is similar to the above, but just iterating different batch size. And then model number 5 is also same as above, but just iterating more epoch. I set up to 1000 epoch for this one, and it comes up the best result for me with 0.44 for the chain loss, and then 0.458 for the validation loss. And then I use the history saved above to plot out the loss for the 5 models. And here is the loss difference between different loops. This is for the model 1 and model 2. There's a lot of overfitting happening here. And model 3, there's really bad result loss here as well. And then this is a model 4, and this is the last model that I have. As you see here, that this is the summary of the model: 2 layers LSTM, 2 layer dense, and then this is the comparison between the actual value and the prediction value of the temperature. And as you see, the pattern is really similar. And the last part is just print out the prediction values to a CSV and submit to Kaggle. Thanks for watching. That's it for the presentation.